Thank you very much. I'm very happy to be here, and I was one of the organizers of the second edition of IMAMS, and it's so nice to see that the conference survived over many years. It was in 2012 and in Pisa, and that the younger generations took it over, and the conference is so successful. So I will be briefly talking about some computational approaches to astrochemistry. And I will start from this slide. So these slides usually one need to be updated very often, because now we are detecting so many more molecules are detected in the space. So now it's over 310. And in particular, I will highlight these two molecules, so methyloxyrene and this benzonitrile, which I will be talking, will be one of my examples in the next slides. But what is the most important, that these complex organic molecules, and in general the molecules so far, were mainly detected based on the rotational features in the microwave range. But this situation is starting to be changed, and this is to the large extent to the James Webb Telescope, and also to some other things like Perseverance rovers, which is on the Mars. So we are starting to have era when these vibrational transitions and vibrational signatures are becoming more important, and we have already some talks showing us these issues. So this is experimental data, a lot of data coming, and what we are needing to analyze of all of this. And from my point of view, we are needing also computational support. And what it means that we can support the experiment in the laboratory, which after are compared with the direct measurements. But we can also, by computations, maybe provide some, complete some data, or obtain the data which are otherwise difficult to obtain, provide different resolution, provide different temperatures, different conditions. So I will be talking about simulation of vibrational features, so essentially from the mid-infrared up to the photoelectron spectra, and to do it where one can consider anharmonic calculations for vibrational features and the vibronic calculations. So all of these computations will be shown are done by these models which are implemented in Gaussian. So they are set starting from the harmonic approximation. So in all cases when harmonic approximation is completely failing, they will not work, of course. But I would like also to highlight that these models have these implementations actually has a lot of features which let you to play around. So like get rid, for example, of some low amplitude motion by reduced dimensionality schemes if these motions are not important for you, but you will just spoil your calculations. So this implementations is just a lot of models which you can set up based on your needs, and these models are still in the development. In particular, Julien Blonneau is still working, and we are working on the implementation also like mixed models with internal coordinates to the couple thing. So it is like long story. It is not the end of the developments. What is now available. So from the electronic structure point of view, I always think that we should use the different methods. Let's say combine the different methods to get as good results as we can, and this, depending on the size of the molecule, can start from the couple cluster MRCI up to the DFT or DFTB, even at some cases like XTB. Combining the single point for energetics, for the conformation, for the differences of conformation of the single transitions, or the gradients and the second derivatives, so harmonic structures and frequencies, and the equilibrium structures, and then higher order derivatives are needed for the harmonic part. And in this case also can happen that the properties cannot be calculated at some level because they are just not implemented. The second order derivatives are analytically are not implemented for some properties. So I will be showing on my slides the different combinations of different methods, and I will not tell anything about it, but you can see what I'm using, and it's in general this depends of course on the size of the molecule. So starting from the small molecules, oxylan and methoxylan, we can simulate the anharmonic transitions, and in particular what I'm showing here are the results which are obtained using always the same part, the same method like couple cluster with complete basis set limit for the harmonic part, and different levels of calculations for the anharmonic part. And actually the accuracy of all of these models is almost the same. So we can really, we don't need to spend so much time and computational effort for the anharmonic part, but it's definitely worth it to put an effort for the harmonic part to push to the limit. And I would like also highlight that we have quite good agreement not only for the vibration wave numbers, but also for the intensities. And another thing which I would like highlight, that even that we have experiment from the high resolution spectroscopy, some places are still were missing. So we are still providing like additional information for these molecules, which is oxyran, which is very small molecule and well known. The similar agreement we can get for methyloxyran. This is possible to do essentially the same level of the calculations. And then using this data, one can ask yourself the question, okay, so let's simulate the emission spectra and compare it to, for example, to this unidentified infrared spectra, which of course are assigned to the polyaromatic hydrocarbons, but there are also some parts which are, for example, like this one in 11.2 microns, which is corresponding to COC deformation. And it actually matches quite nicely. And this is some feature which is not in the fullerene, or we don't have this kind of bending. We can also compare the spectra between the protonated oxygen and oxygen, and based on these simulations, we can say that, okay, the spectra is different. Moving to bigger molecules, this can be like DNA bases and, or amino acids, which none of them were actually yet observed in the interstellar medium, but they were found on the meteorites. Now example of this benzonitrile, which was detected in the interstellar medium based on rotational features. But if we want to look at it also based on the vibrational features, we can actually simulate these bands very, very nicely within 2 reciprocal centimeters. And based on this, we can also provide some predictions of the spectra in the near-infrared region and the higher overtones. Similar simulations can be done also considering pieces which contain Fermi resonances with very nice agreement with experiment, and this can be applied also for the other molecules like thymine and thymine cation, and again looking if we can distinguish between these 2 molecules, so the neutral and cation based on these vibrational features. Simulation of near-infrared spectra also very important for the analysis of experiment, which are mice soil analog samples. This is the type of experiment when, which is needed to analyze what was going on in the detection, let's say, of the organic molecules on Mars, and also to guide where this robot should go. So my colleague Teresa Fornaro, she's looking at which minerals would be preserving eventual organic matter. So they are doing experiment mixing of different organic molecules with different minerals, and all the detection is in near infrared. And to do any analysis, one needs to know anything about this near infrared spectra, and it is usually not available in the literature, so analysis can be starting from the computations. Moving to the vibronic spectra, we were talking already about it in this conference. We have some spectra in the broad energy range, and one of the questions is which is the transitions. If we do the vertical energies, we really sometimes don't know which transition is actual, which band is corresponding to electronic transition, which is some to the vibrational features. So these simulations, when we can really distinguish and simulate the whole band, as can be useful, and this can be done, say, based on the same simulations. We can do based on the same calculation, we can simulate spectra at high resolution and low resolution, and we can also add something like hot bands with quite nice agreement with experiment. And also due to availability of second order analytical derivatives of TTDFT, nowadays one can do also anharmonic calculations in excited states. So we can do anharmonic calculations in both states, correct the vibrational energy levels in both states, and obtain some better agreement with experiment. This can lead to better analysis or more detailed analysis of experimental spectra. So here is the photoelectric spectrum of timing. So experiment, as you can see, is not highly resolved. We have good agreement with experiment, but we can also assign the spectrum, and also in principle we can simulate the spectrum of the higher resolution, which might be of interest, and we can also simulate spectra in different temperatures, which also can be of interest of different environment. So with this I will finish, and I think that we have the model which at least can be useful for the prediction of vibrational energy levels, and we have the accuracy of models, we have non-fundamental transitions and reliable shape of the electronic spectra, and also this type of computation I believe can also be used to fit some artificial intelligence models if needed. And here's my references, and I thank you, my collaborators, and thank you for your attention.
Thank you very much. We have a bit of time for questions. Yeah.
Thank you. Very, very interesting talk. So there was a moment, I think you mentioned about anharmonic spectra calculation, IR spectra in the excited states, but it was very, very quick. Could you tell a little bit more about it? So can you do it with hybrid or double hybrid functionals, for example?
So double hybrid are not well implemented, I think, for TD. I think that the codes which have implementation of second order derivatives of double hybrid in TD-DFT framework are not the same codes which have anharmonic calculations. So, so with double hybrid, I think the Gaussian don't do TD-DFT with double hybrid, and I think Orca and others doesn't do the analytical second derivatives for the double hybrid TD-DFT. So this is the small problem here.
Yeah, but it works with the hybrid ones, right? With
hybrid ones it works, but nobody yet benchmarked it, so I'm still planning to do it because it requires some data. So I cannot say that the accuracy which we have for say B3LYP is the same for the excited states. But this result with this Wien radical shows that it's big improvement if we do anharmonic corrections.
Mm-hmm. So for some weakly bound states, it could be a problem, right? If they are very anharmonic.
If weakly bound states is generally a problem, but it depends also with which spectrum you have, because if you don't observe the spectrum in the lower energy region, maybe you, what I'm usually doing, if I have some vibrations which cannot be treated at VPT2 level, we can exclude them from VPT2 treatment, and if your spectrum is anyways measured about 500 reciprocal centimeters, this usually works nice. So this is the trick.
Another question?
Thank you for the beautiful talk. I probably missed your last sentence about machine learning, artificial intelligence methods. Would you like to create these models for predicting spectra using, for example, the geometry or any other features of these molecules?
So I personally don't want to do anything, but I know that the people are interested to just generate a lot of data but for many molecules based on the computations, and this will allow to create a database, and the people are using such kind of database also to improve machine learning. The important part is that very often the experiment, at least for many molecules for which we know the spectra, we actually don't have the whole coverage of spectra. And here we can, if we calculate the spectrum, we can assume up to 3 quanta that we are providing all the transitions. So it can be used for them, is better training set than experiment. Let's say, unless somebody will redo experiment for most of the molecules, which I'm suggesting, but it's not publishable. So it is kind of like guidance for any type of this kind.
Okay, thank you.
Sorry, no. So there's no implementation at all in Gaussian of machine learning for IR spectroscopy?
Not that I'm aware of.
Ah, okay. No.
measured?
So
how has it been detected on rotational transitions?
yeah,
or-
that was detected by rotational transition, but it's expected that it could be also detected on by vibrations now with the James Webb. So it's a lot of actually computations because this benzonitrile. Some people say there was a measurement of the spectrum just 2 years ago of all the spectrum and also electronic spectra and so on. But for all the other bigger molecules which have been already observed, there is actually no experimental data. So this is like now it's a lot. Everybody's calculating these molecules to provide some data for James Webb.
Okay.
Okay, yeah.
Sorry, short question. So the data will be available to anyone who would like to be interested on.
So actually, within this cost action, we are creating. So I'm not providing here the website, but I can give you. So we are planning to create. We are creating, let's say, the database and combining also different of already available. So we are probably going to do like a links to different database. So I usually when I'm publishing these molecules, I'm just giving the supplementary material which is listing all the lines and intensities, and I'm asking experimentalists to do the same.
Okay. So there's no. I ask because I really ignore if there. So there's no centralized.
There are some
efforts
databases, but I think this is not really like super centralized as far as I know.
Thank you.
Yeah, it has some potential. Interesting. Any other questions? Else, let's thank the speaker again. Thank you very much.